So I'm going next. Again, my name is Heather Emady. I'm an assistant professor in chemical engineering at Arizona State. And I'm going to be talking about modeling granular heat transfer in a rotary drum. So I've heard a lot of talks mention heat transfer, so this is going to focus solely on heat transfer, so hopefully you'll find this interesting. And I'm going to be presenting the results from my PhD student, Manogna. So she knows all of the intricate details, and I'm presenting an overview of this. So what I'm going to go through in my talk is an introduction to the problem, the approach to solving the problem, what are the existing heat transfer models out there, and then some initial results, trying to validate conduction heat transfer, and then looking at the effects of model and operating parameters. Then I'm going to end with a summary, and if there's time, I'm going to present a couple very preliminary slides on new work. Okay, so first the introduction. So conduction, convection, radiation, heat transfer occur in so many different multi-phase processes. And there's a couple different approaches to looking at these. So if we look at simulations, we now have seen particle-particle conduction to be pretty common in DEM codes. So I'm actually going to focus very much on the granular phase. So the main focus is DEM. So particle-particle conduction is very common, but that's pretty much it. And the problem with codes like this that are just DEM is you have to couple the fluids separately, and then that gets really complicated since different kinds of heat transfer involve the fluid phase as well. So another a code that I'm interested in looking in, mainly because I got funding to do so, is MFIX DEM, which Ting Wen talked about a lot on Monday. So it's the CFD DEM code developed and maintained by the Department of Energy, National Energy Technology Lab. And it's nice because it's open source and it's DEM and CFD in a single code base. So it allows those that framework to do these models that involve multiple phases. So that's on the simulation side. For experiments with heat transfer, it's very difficult to get experimental data. I spent a lot of time trying to look in the literature. It's very hard to find, and a lot of that is because how do you measure temperature? Often by thermocouples. You have to stick thermocouples into the process and get some sort of averaged temperature. So that's an overview of heat transfer. The system that we're going to use to study heat transfer is a simple rotary drum because it's simple, but it's also very widely used in so many different industries, like for drying, mixing, granulating, coating, and heating. So as a more specific industrially relevant and energy relevant case, we're going to look at a calciner, which is just basically a very long rotary drum where you have your particles coming in here, heat's being applied, the drum's rotating, there's usually some reaction, and then the particles come out. Sometimes you have a gas phase injection from the opposite end. And so this is often used in calcination, which is used to make catalysts, and calcination is also used to make cement, which is in literally everything. So actually about 5% of the world's energy is used in the calcination of cement. So if we can better understand this seemingly very simple process, then we have a great potential to reduce energy consumption. So if we look at a bunch of the variables involved in this type of process, we have, oh no. Okay. It seems like the pointer should be that button. Okay. So we have particle physical properties. So every property of the particle you can imagine. I just listed a few here. Particle size, shape, size distribution. Thermal properties, since now we're doing heat transfer, so what are all of the particle thermal properties that are important? And then depending on what your system is, so these are system parameters that are relevant to rotary drums. So how much fill level level do you have? What's the length of the drum, the diameter, tilt? Sometimes there's baffles to try to promote mixing. So all of these things affect heat transfer. And it's really difficult. Right now we have no idea in general how any of these really affect the heat transfer. So what happens right now in industry is they've just been doing it for a while. So you put whatever in, you get what you want out, and you don't really know what's happening in there. Okay, so the big picture overview of this work, and this is just, and I'm just going to present a start to this, is we want to quantify granular heat transfer. That includes conduction, convection, and radiation in a rotary drum using both simulations and experiments. And the hope is that we can align both of those so that they can match. So how are we approaching this? This is a setup we just built at ASU. It's just a stainless steel drum where we have windows here where we can see the particles inside. And here we're heating the drum on the outside. Right now we're using these very inefficient heat guns. And we're working, it's such a long process to try to get a good system built, but we're trying to get a better induction heating system because we eventually want to do radiation. So right now we're just doing pure conduction here with this setup. And what we can do here, so we can use high-speed video, look at the granular flow happening, see if there's any changes due to temperature. We also got this really cool thermal IR camera where we can actually see individual particle temperatures. So this is going to be really useful to be able to directly compare individual particle temperatures to simulations. And if you think about how people have been doing it up until this point, we also have thermocouples. So if you can see these tiny dots, there's probably like 2 maybe thermocouple ports here. So if we're just taking temperature measurements with thermocouples, we would just get 2 numbers, whereas with this nice camera, we can actually see all the particles that are on the edge of the drum. So the idea is to directly compare these experimental images with our simulations. And I mentioned we're primarily using MFIX because of the funding and because they do have all heat transfer modes in there. So let's take a look now at the existing heat transfer models that are available and used in these codes. And I also want to mention too, I am not a hardcore modeler like most of you guys. I just use the models. So hopefully this will be motivation for some of you and help you on different directions to improve these models. So if we look at just indirect heating, so again, just from the outside of the drum, we're just looking at the heat propagating to the solid bed and then the particles exchanging heat with each other and with the wall. So for conduction, so these are all of the different kinds of heat transfer and all of the subgroups between the particle and the fluid. So there's lots of different kinds of heat transfer that need to be taken into account. Radiation becomes really important above, like Ray said, above about 600 degrees C. So below that, it's pretty much, for dense phase systems, it's pretty much conduction dominated. So to start, we're focusing on conduction. So the particle wall and particle-particle conduction, but we eventually do want to get to these other stages. So these are the heat transfer equations. So the internal energy heat equation for a particle, where we have the contributions of the particle wall and the particle-particle contact conduction there. And so that's what's in the model. And then we can get the heat transfer coefficient if we do a heat balance on the rotary drum system. Okay, so if we look at our rotary drum, that's at this wall temperature TW and at this average bed temperature TS, we can do this heat balance that will give us the temperature distribution as a function of time. and as a function of different particle parameters, drum parameters, and then we also have our overall heat transfer coefficient. So the overall heat transfer coefficient is what we're trying to get here. So we can lump these together and plot this temperature versus time to get this slope, and so from there we can get our overall heat transfer coefficient. Okay. So taking that, when I first got into this problem, I was a postdoc at Rutgers, and we were working with some catalyst companies who were really interested in the time it takes for their particles to heat up in this kind of system. So that got me interested in trying to figure out heating timescales. And if you think about it, for something like a catalyst, you want it to heat. You want all the catalysts to heat up at the same rate and come out and be uniform. And so the first one is the thermal time constant. So from that heat balance equation I just showed you, where this was the slope of the temperature versus time, we can lump this together into tau, which is the thermal time constant. So that's related to the time it takes the entire particle bed to heat up. We can also do a heat balance on a single particle. So if you just put a single particle sitting on a hot wall, the thermal time constant there. And then the contact time, so the time that a particle spends on the wall, which is related to the fill level angle and the rotation rate. So we identified these as the main time scales that are important in this type of system. And we came up with this very nice looking relationship that plots the thermal time constant overall divided by the contact time versus the particle thermal time constant divided by the contact time. I can't tell you exactly why this works. I tried every combination of those different time scales. But basically we come up with this very nice relationship over a range of thermal conductivities and also rotation rates. And what we found is that there's different sort of heating regimes. So at this lower regime here, the particle bed basically heats up like a solid body, where you have this temperature gradient, hot at the wall and then cool towards the middle. In this intermediate regime, we have the particles heating along the outer layer and a cool inner core. And then up at this higher region, we have the particles being very well mixed. So for something like the catalyst industry, they wanted something more like this, where they knew the particles were heating up very uniformly the whole time. Another interesting thing to point out here is these two snapshots are at different thermal conductivities and different rotation rates, and they align on the same spot to get the same heating profile, which was interesting. A couple things to note here. So this is a really cool result. It's only valid for this certain fill level. So we did a 13% fill level, and for this particle size distribution. So we did a mean diameter of 4 millimeters, and we did a normal size distribution. So from here, I've really been wanting to, and this was all just doing DEM simulations. So from here, first I wanted to really validate this with experiments, because we have no idea how accurately this really represents experiments, and then to try some more conditions that we know will be important, like fill level is obviously going to have a huge effect, as well as particle size. Okay. And then so looking at the software, this is by no means a comprehensive list, but these are just the tools that I'm using, and I just want to compare them briefly here because I'm going to be presenting results using both of them. So EDEM is the commercial software. It's what I used in that slide I just showed you. I mainly used it because I didn't know anything about simulations. It was the easiest to use. It has particle-particle conduction, and then at Rutgers we had our own code to do the particle wall conduction. But that's basically all you can do since it's just pure particles. So you would have to couple with a CFD solver to do like convection. And then we have MFIX DEM, which has all modes of heat transfer models all in the software already. But one thing is they haven't yet been validated. So they were pretty recently implemented and tested for a 2-particle system, but they haven't been tested for a even lab scale system. So our current objectives under this big picture goal of quantifying granular heat transfer in a rotary drum. First, we set out to validate contact conduction in MFIX DEM, and then to look at the effects of model and process parameters. So we know different process parameters have various effects, but at this stage we were also really interested in looking at model parameters, especially because we were looking at 2 different codes. So the main things we looked at were rotation rate, particle size distribution, and rolling friction. Okay, so the first set of results is validating conduction heat transfer, and it was really difficult to find experimental data in the literature. We found one paper that we were able to extract data from, so we just tried to replicate those experiments with these simulations. So these are MFIX simulations. It's 50% fill, because that's what the paper did, 6-inch diameter, 3-inch long, 2 millimeter diameter alumina particles, and the rotation rate here is 20 RPM. And here we have the heat transfer from the wall to the particle bed. These are all of the simulation parameters we used here. And what we see, as we expect, as time progresses, the temperature increases. And like we saw for that intermediate heating regime, the particles are heated on the outer layer first. And then there's a very cold core in the center. And so what we get from DEM is we get the temperature of each individual particle after each time step, and from there we take that data and we calculate an average temperature. And so to compare this with simulations, or to compare the simulations with experiments, we got this figure. So the red is our simulations, the blue is the experimental data from that paper. And we actually got really close results that we were very happy to see. They aligned so well, but the experiments look a little interesting. Those were published, so I didn't do them, my students didn't do them, and there was no confidence data on these, so we're not entirely sure how reliable they are, but at the same time, it is promising that there's such a close match. But in moving forward, we were interested in thinking about, so if we look at comparing experiments and simulations, what are going to be the issues there? So that's how we decided the next steps of what effects of what parameters to look at. So to do this study, we used a slightly different system, same geometry, but it's a little bit of a hotter wall, so a couple 100 degrees Kelvin hotter, and we have a 13% fill with 4 millimeter diameter particles, alumina particles, and we actually used the work, the simulation information from the paper I published earlier, just because we had that information and we wanted to compare EDEM with this MFIX heat transfer. So these are the model parameters, the simulation parameters. Okay, so there's a lot of stuff here. The first thing I want to note is we're looking at heat transfer in a polydispersed bed. So EDEM already had polydispersity. We just ran those simulations with the particle size distribution. And actually, when we started this project, MFIX didn't have polydispersity. And actually, as part of our funding, my co-PIs and I developed that capability. So the goals of this was twofold. So it was to test the polydispersity and also the effects of heat transfer. Okay, so we compared this to my paper results. So this is the overall heat transfer coefficient as a function of rotation rate. As you can see, there's very little effect on there's very little effect of rotation rate on heat transfer, which is interesting, especially above 10 RPM. That's very apparent. I do want to point out, though, that with lower RPMs, there might be a bigger effect, and that's something that we're examining in the future. Okay, but if we look at the difference between these two, so our new MFIC simulations, my previous work, there's the same trend, which is promising, but there's also this gap. So we were trying to figure out what's that gap from. So we identified a couple things. The first is rolling friction. So EDAM has rolling friction, MFIX doesn't. So that could attribute to the difference. And also particle size distribution, we learned was a lot trickier, and I'll present a few more slides on this. So you can input the mean and the standard deviation and the type of distribution, but beyond that, the simulation determines its own distribution from that. So it's not going to be the same exact particle sizes. One other thing I also identified is for the previous work, we actually had our drum tilted a little bit just because normal calciners are tilted. So that's another difference here. So we decided to run our own. So using EDAM on our own and MFIX running a new set of simulations, we still get, it looks a lot closer, but it's still a little bit of a discrepancy. And so we really wanted to investigate more this effect of particle size distribution. So what we did is we ran 3 different simulations putting in the same particle size distribution information, so the same minimum, maximum, mean, and standard deviation, and we got 3 slightly different distributions. And so we wanted to see the effects on the overall heat transfer coefficient. So these are the results. So they look pretty close, but there still is some difference. So there's actually about a 2% difference, which is interesting because you think you're running the same simulations if you're putting in the same parameters, but you're going to be getting slightly different results. And this is something that's interesting and something to think about when you're trying to exactly replicate your experimental particles in your simulations, that there might be some issues there in trying to replicate the exact distributions. Okay, we wanted to look at this just a little bit more, looking at the breadth of the distributions and that effect on heat transfer. So we have a homogeneous distribution, so same particle sizes, a narrow distribution, and then a broader distribution. And we looked at the effects on the overall heat transfer coefficient. We found that the overall heat transfer coefficient decreases as the particle size distribution broadens, and then between your homogeneous and your broad distribution, you have about a 9% change in that overall heat transfer coefficient. So this just further shows the importance of the particle size distribution in heat transfer. Okay, the next thing we wanted to look at was rolling friction, and we couldn't test this with MFIX because it didn't have it. So we wanted to see how much it really matters. So we looked at EDAM, and we used values from 0 to 0.1 rolling. So 0.1 is kind of on the high side, but we wanted to use a range that people have used in the literature. And what we found is that the heat transfer coefficient decreases when you're increasing the rolling friction, which makes sense because when you have low values of rolling friction, you have better particle circulation in the bed. And so we found this effect to be significant above 0.01, so somewhere in between 0.01 and 0.1, there seems to be a big effect there. Okay. So now I think I have a few more minutes, so I'm going to summarize and then present a couple very preliminary slides. So we looked at conduction heat transfer in MFIX. We validated this with some literature data and looked at the effects of model and operating parameters using simulations. We found that rotation rate doesn't have a significant effect. and particle size distribution and rolling friction are important, and we identified that MFICs didn't have rolling friction, and we do think it's important for heat transfer. So moving forward, we want to look at convection and radiation and perform our own local experiments. So I want to present this as a very preliminary test of all of the heat transfer models in MFIC. So we just wanted to do a quick test to see how they all behaved, and these are all the parameters we used. So we did identify that we really didn't get the radiation effect. So that's something to look into, is the models, the heat transfer models in MFICs are very basic and definitely need to be tested, but what's nice is the framework is there. So it'll be interesting to compare this against experimental data. And we did some experiments. So we looked at, just for contact conduction, we looked at a fill level between 4 and 10% and rotation rate between 1 and 9 RPM. These seem like really low values, but these are actually really industrially relevant values, so we wanted to look at those. And what we found, so we just recorded the temperature after an hour for each of those conditions. This is when we just got our setup, so we did stop the drum and stick in the thermocouples, and right now we're still working on the calibration of the thermal camera. But what we found is that that we can achieve a higher heat transfer rate at lower fill levels, which makes sense. You have less particles, they're going to heat up faster, and then also at higher rotation speeds. So if you remember before, there really wasn't a big rotation speed effect, but it's a little bit more now at these lower rotation speeds below about 10 RPM. So this was just an initial experimental study to look at these, and moving forward, like I said, we're going to do more conduction, get our thermal camera up and running, and then try to move on to convection and radiation. Okay, so I'd like to acknowledge funding from DOE NETL and my co-PIs, Aitiken and Yang, both from ASU, and NERSC and Exceed for computing resources. This is my research group, and this is Manogna, who did all of this fantastic work. So thank you all for your attention. Huh? She just is in all the photos.
I have a couple of questions.